Hello, and welcome to a video about the quiz review. All right, let's get started. Number 1. From the following sequence, let's write an explicit formula. Okay, so first, let me write down what the explicit formula looks like. So the explicit formula looks like this. It's AN equals A1, whoops, I wrote a dash by accident, and then in parentheses R, n to the power of n minus n 1. Wow. Anyways, A1 represents our first term. Beautiful. So A1 is 1. So the first thing I'm writing down is 1. Now R represents our ratio. In order to find our ratio, we're going to take the second term, which is 4, and divide it by our first term, which is 1. All right. Once you divide, we get our ratio. In this case, it does end up being 4. That's just what it is. So that's the next thing I write down. And then the power stays as it is, n minus 1. Let's try that again. All right, number 2. A1 is 7. To find R, we need to take 7, our first term, and divide it, or take the second term and divide it by our first term, is what I meant to say. So negative 70 divided by 7. When we do that division, we get negative 10, and that becomes our ratio. And that's it. So our formula is 7, and then in parentheses negative 10. We close those parentheses and give it a power of n minus 1. Okay, not too bad. Let's continue. For number 3 and 4, we're going to use the explicit formula and rewrite it in function form. Now, function form looks like this. It's f of x equals a times r to the power of x. Now, r is the same r as in our explicit formula. It's our ratio. So that's not too hard to find. Now, a is not the same as our a in our explicit formula. A is actually the y-intercept. So the way we find it is by plugging 0 into our explicit formula. So this is what we'll do. In our calculators, we'll type 10 parentheses 1/2 and raise it to the power of 0 minus 1. So instead of n, we put in a 0. Now when you type this into your calculator, you should get 20. So a is 20, r is still 1/2, that doesn't change, and I raise it to the power of x. Let's try that one more time. Our r is the same r as our explicit formula. And to find a, our y-intercept, we're going to take this formula, negative 4 times 1/5, but instead of to the power of n minus 1, we're raising it to the power of 0 minus 1. Okay? Hopefully you've typed that into your calculators. When we press enter, you should get negative 20. So negative 20 times 1/5 raised to the power of x. Okay, not too bad. The hardest part, I think, in number 3 and 4 is entering it into your calculator correctly. Okay, number 5 and 6, we are comparing two exponential functions in different forms. One is a table, the other one's a formula. We want to see which one has the greatest constant multiplier. Now, our constant multiplier, and now this sounds silly, is the number we keep constantly multiplying, which is going to be our ratio. So the easiest one to see is function b. The ratio is 9. Okay. Now, for the table in function a, to find r, our ratio, aka our constant multiplier, what we're going to do is similar to what we did in number 1 and 2. We're going to do second term divided by first. So, whoops, I just picked a black highlight. Why is that even an option? That's just bizarro. Okay, let's do this again. 11 is our second term. 11 over 10 is our first term. Let's divide. So in your calculator, you would type 11 divided by 11 over 10. Once you pressed enter, you should get that r equals 10. All right, so this is part of explaining your work. You're showing me that you're identifying these ratios, these constant multipliers. Now we're going to pick which one has the greatest one. Function A has 10, function B has 9. 10 is greater than 9, circle function A. In mathematics, this is explaining our reasoning. It's showing our work. Let's do the same thing in number 6. In function B, our constant multiplier is easy to see. It's 4. For function A, we're going to have to do some division. We're going to take our second term, which is 3, and divide it by 3/5, which is our first term. When you type that into your calculator, you should get 5. 5 is greater than 4, therefore function A has the greatest constant multiplier. Onwards we go. Okay, now what we're going to be doing to these 4 functions, which all happen to be the same function, is translating them. All right, so for number 7, we're asked to take function g of x and translate it 10 to the right. Now, when we're going to take a function and we're going to translate it 10 units to the right, we attach that into our exponent. So we write x minus 10 as our exponent. Minus represents movement to the right. I know that's a bit counterintuitive, but we did prove it during our lessons when we did those graphs. So subtracting from the exponent moves our function to the right. Number 8, let's move that same function to the left. So if adding to the exponent is a movement to the right, wow, I said that backwards. What a morning for me, huh? But 7 minutes in, I'm not re-recording. I'm just going to start my sentence over again. I hope you're okay with that, my friends. If subtracting from the exponent is moving to the right, then adding to the exponent is moving to the left. Boom. Now, a little way that I remember where to add and subtract for left and right is that on our graph, the x-axis is the one that moves from left to right. It's that horizontal one. So if we're going to move either left or right, we have to attach it to the actual x. Again, I know it's counterintuitive to subtract for right and add for left, but that's just something you're going to have to remember. It pops up again in any other transformation that you're going to be doing for any other graph, and you're going to be doing that in the next following years of your mathematical careers. So yeah, that's just a trend that you're going to have to keep up with. All right, number 9. We're going to now translate the same function up. Now, when we translate up, luckily, it's very intuitive. We're adding, and we're adding outside the function, so not in the x. Well, if adding moves you down upwards, my goodness, then subtraction moves you downwards. Now, the way I remember the movements up and down is that if we are to graph a function and move it up and down literally, we're taking the whole function and kind of in our imagination pulling it up or pulling it down. So I imagine in my head the whole function, and then on the outside I'm either pulling it up or pulling it down. Now I don't know if that works for you at all, but that's how I memorized it. Maybe it will help you too. Speaking of literally taking a function and moving it, let's do that in number 11. Now, in number 11, we're going to take our function and we're going to move it 2 units down. The way I pick the movement is I pick 3 points on our graph. I like to pick one on the left side, one on the right side, and then the y-intercept. We're going to take this whole graph and we're going to move it down 2 units. Let's do it. So each point will be moved down. 1, 2. New point. 1, 2. New point. And 1, 2. New point. Now the reason I choose these 3 points is because I want to make sure to move the whole graph, perfectly. And by picking one on each side and one in the middle, it just seems to give us a good representation. Now don't forget to connect your dots and draw that little swoop. And that's that for number 11. If you have any questions, of course, let me know or ask your teacher. Otherwise, have a wonderful rest of your day. Bye.